We're going to be graphing and solving quadratic inequalities. That's with a less than symbol, a greater than symbol, less than or equal to symbol, or a greater than or equal to symbol. Let's just jot down some ideas that we remember from this, or possibly forgotten. Anytime you had a less than or a greater than symbol, we dealt with dashed. Well, in chapter 3, we dealt with dashed lines. But these will be dashed parabolas. But when you have an equal to symbol, these will be solid parabolas. Steps for any inequality. This is a good review for final. Any inequality, you have to draw the boundary. Whether it's a line, whether it's a parabola, whether it's a cubic function, you draw the boundary according to your strategies. It's either going to be solid or dashed depending on the inequality sign. Then you choose a test point, not on that boundary. You have to choose a test point somewhere to determine if it is a solution or not. You shade on the side of the boundary where the solutions are located. So if you get a true statement, you shade on that side of the boundary. If you get a false statement, you shade on the opposite side of that boundary. But whenever I say sides, it's nice to say sides when you're dealing with a line. When we're dealing with a parabola, you're either going to shade inside the parabola or you're shading outside the parabola. Let's go to quadratic graphing. The reason why I put this up is from warm up. We know our strengths at this point. We know how to rewrite quadratic equations in vertex form. We know how to rewrite quadratic functions into intercept form. You just didn't realize that's just factoring. We also know how to find x-intercepts by setting an equation equal to 0. So let's go to this example. We're going to graph it in some way. Let's put it into vertex form to find the vertex. So algebra way, I add 9 and subtract 9. When I add 9, that's going to be part of my completed square in the next step. So I have a complete square, x minus 3, quantity squared, and then I have minus 4. We put it into vertex form to find immediately the vertex. Graph it. And let's put in that axis of symmetry. Ooh, wait a second. Maybe we have to just visualize where that axis of symmetry is. Because I just realized if I put that dashed line in there, it might confuse me with, hey, wait a second, where's that boundary at? So rewrite in intercept form from the original. So multiply, add. What multiplies to 5 adds to negative 6. Then I say, okay, if I'm trying to figure out what are the x-intercepts, what would make each one of those 0? I graph them. So typically we would do a t-chart to find another set of points, but why don't we just find the y-intercept? So last set of points, y-intercept, if I plug in a 0, I'm left with just a 5. I plot that point and locate where the axis of symmetry would be. Typically the axis of symmetry, if I would have drawn it, would be here. So it's 3 away. So I'm going to draw another point 3 away on the other side. When I connect my parabola, I've got to recognize, hey, wait a second. Am I going to be solid or dashed? We just got our boundary. Now we're going to choose a test point. Let's test 0, 0. Why would I test 0, 0? It is not on the boundary. So we choose it as a test point, plug it in. So testing 0, 0 is 0 bigger than, well, that 0 is at 0. I'm left with 5. So we get a false statement. you ask yourself, do I want to shade on this side of the parabola or not? So shade inside the parabola. When we get this into vertex form, we're going to have to take a negative out of the first two terms and leave that amount of 3 outside. This is really hard. So now, just in those parentheses, how would you, what would complete that square? Notice how I added 1 to the completed square and subtracted 1, but notice how it's still in parentheses. Oh man, this is really hard. These 3 terms are the only thing that complete the square. How do you get this guy out? That's the question. We have a negative, -1, so a positive 1 is going to be outside. So vertex form, y is less than or equal to negative x minus 1 squared plus 4. We now have it in vertex form. 4, and we graph it. We realize, hey, wait a second, that axis of symmetry is going to run right through that vertex. Now let's find the intercept form. So if I were to start solving, I'd probably divide everything by -1 or move everything to the other side. Either way, you still get x squared minus 2x minus 3. 0 divided by -1 is just 0. So y-intercept 0, 3, and then it is mapped to another point on that axis of symmetry. You ask yourself, solid or dashed? So we chose test point 5, 0. We plug it in. This becomes what? The opposite of 25. So -25 plus 10, we're at -15. Plus 3, we're at -12. Is 0 less than -12? It is not. So where 5, 0 is, we don't want to shade on that side. We want to shade on the inside of the parabola. So what if we had quadratic inequalities in one variable? We will solve to find boundary points, but we're just going to put them on a number line this time. Because if we only have one variable, that means we only have one axis, no longer 2. And then we still pick test points, plug them in, see if they are true or false to determine where we shade. Okay, first one up. We solve. We can solve this. It's equal to 0. We have several strategies. We could factor. We could complete the square. We could quadratic formula it. So we just factored, and again, you have to figure out what are your boundary points. We're only doing this in one variable. So I'm not going to write it as a point 2, 0, because I don't have 2 variables. This is just 2 and 3. Those are my boundary points on my number line. After we graph our boundary points, pick test points. Like pick a point on this side of 2. Pick a point on that side of 2. We could choose 2, we could choose 1. We could also choose, I'm going to say 0. You can choose 0. If I plug 0 in, I get, okay, so is 6 bigger than or equal? Is 6 bigger than or equal to 0? Yes, so I would be shading this side of 2. Let's just think about for a moment. If this was a parabola, don't draw this, but just watch. Just watch the screen. If this was a parabola in 2 variables, so instead of that 0, there would be a y. This is what my parabola would look like. Notice where we shaded. We shaded outside of the parabola. What area would also be outside of that parabola? How to write our answer? Back from chapter 1. We have the solutions less than or equal to 2, or the solutions bigger than or equal to 3. That's how we would write, if I have this graph, we would write the statement using an or. So for this, just to recap, can't use factoring, nothing multiplies to 5 adds to -11. Cannot use completing the square because it'll get ugly. Take an 11 divided by 2. Can't use a square root method. We have to use quadratic formula. So we found our boundary points, but how would you put that on a number line? I need approximations. So we physically plug these into our calculator so that way we can at least see, okay, where does 0 lie? So if I were to test 0, notice how 0 is actually on the outside. 0 would be on the outside. My bad. This should be 0 or 0.48. But 0 would be here. If I test that, is 5, because I plug it in, my bad. I plug it in. 0 minus, this becomes 0 plus 5. So is 5 less than 0? It's not. So I would not shade there. So think, if this was a parabola, and you don't have to do this, but if this was a parabola, I would not shade on the outside of it. I would shade inside it. So I've got open circles because of the inequality sign, and I would shade in between. Let's talk about how to write our answer. So when we shaded something in between, we use this symbol, and then this part, 11 minus root 101 divided by 2, that's the smaller number. And this 11 plus root 101 was the bigger number.